much here. I always enjoy to visit Moscow. So thank you also the university for the invitation. So this is the title. This is a joint work with Sabir and Alejandro Melle. Okay, and it will be a kind of survey of our work in power structure, and I will use this like a kind of tribute to the my co-authors. So here you have a picture of my two co-authors, Sabir and Alejandro. You recognize the place, no, Sabir? Yes, it's Mallorca. Okay, and also I want to pay tribute to Alejandro. That you know he has a neurodegenerative disease in an advanced stage. So that's for this reason Alejandro cannot be here. So I wanted also to pay tribute to him, that was really do a lot of work and is responsible for all I'm talking about with Sabir. Okay, so this is more or less the outline. We have only 16 slides. So we'll talk about power structures that you will see is a way to make exponentiate a series when the exponent is not a natural number but any element of a ring. So originally we call this exponentiation of a function, but now some referee come with the proposal to use power structures, and we use that. And we will talk about power structure, relation with structure, also power structure in the Grothendieck of motifs, of varieties, and application. There is a lot of application to generating function in geometry and also in arithmetic. If we continue, maybe some person in the audience may speak. Where are the singularities? Okay, so the singularity. You see the schedule. The singularities were in the motivation. You remember well, Sabir, that in many places in singularity theory, for instance, in the zeta function, campo zeta function de monodromy, there is some exponentiation or power in which appear the Euler characteristic of a variety, and also in arithmetic it appear in the exponent number of points on a variety that are example of what they call Motivic measures. So there is some additive invariant on varieties. So we just were interested in precisely how to, as I say, to put in the exponent also, like the class of a variety, and the main motivation was a problem related with arithmetic and geometry, namely the Igusa conjecture that related some arithmetic properties, namely the poles of the zeta function contain number of solution of a polynomial with the eigenvalues of the monodromy. So there is this very intriguing conjecture, Igusa monodromy conjecture, and that was our main motivation. And now later on there appear a lot of application of power structures. You will see the last three lines are just application that made it for other person. So, but you also see that there is no trace of this Igusa monodromy conjecture. So, in some sense, we can think this talk is like the chronic of a failure, that with the time become a success. So now there is a lot of application of power structure, but as I say, we fail in our original motivation. Sorry, wait a minute. I'm going in the direction. So, what is a power structure? As I say, over a ring with a unit is a map from from the set of series starting with 1 the ring to the series started with 1. So as I say, it's a way to exponentiate a series with coefficient in the ring to an element of the ring, and that has the usual properties of the exponentiation. So that's the usual properties. Okay, so that the exponential series 1. Okay, that the exponential. You see, they are no need to repeat of them. They are the usual properties. So, for instance, property 6, you see that's also very typical that when we exponential this special series, then the first coefficient is the exponent. So, okay, so this is the definition, and this has to be with lambda structure. Lambda structure was something that okay, I did not say, but we started work around 2003 or 4. You remember, Sabir? 3 or 4. Okay, but at this time there was also some related thing that is called that was considered in many places, what they call wait a minute, lambda structure. So what is a lambda structure in a commutative ring? Is for every element of the ring A, we associate a series that start series lambda. So it's a map that to every element A associates a series. Okay, that start with 1 plus A times t. Okay, plus term times t. Okay, plus term of a higher order, and okay, with this property that for the sum you get the product, and sometimes there is an extra condition also for the series lambda of A times B, but we will not consider that. And then what is the relation with the power structures? You have a power structure. You can take any series lambda of t, and you have alpha of t, and then you exponentiate alpha of t, and it gives you to A, and this gives you lambda structure. So you have, for one power structure, you have several lambda structures. Okay, and in the other way, that you have a lambda structure in a ring, you can for a series you can and a series. Okay, A of t. Then you can put make this the composition of the series A of t as product. Okay, and then in this way, I mean, you get A of t to the end as the product of all these series gives you also power structure. Well, as a resume, in a ring there are many lambda structures, but much less power structure. So, okay, so that's the more or less the initial point. All right. So and now, as I say, we were interested to exponentiate. In fact, varieties. In fact, not varieties, but classes of varieties. So we were working in the Grothendieck ring of complex quasi-projective varieties. That is, remember, is the abelian group K0 of bar generated for the classes of varieties with these relations. So that I mean, okay, if they are isomorphic, we define the same classes, or they are isomorphic class. Have Zariski closest subvariety of y of x, then we have this the composition of the classes. Okay, and as we say, this is make a ring, the Grothendieck ring of varieties, and the multiplication is just given by the Cartesian product. All right, okay, and in fact the most important we say lambda structure we have is when we consider the Capranov theta function. Okay, that for a class of for a variety, you can consider the axiom of the symmetric group on X, the power of the symmetric group, and then the symmetric product, sorry, of X, and we get this generating series. Okay, and this is as I say, this is a lambda structure. Okay, all right. And in fact, we will now see that this power structure leads you again to the Capranov power structure. Okay, so this how do we define geometrically the power structure? So we use as a model for the exponentiation of a series with integer coefficient to an integer. Okay, so you have this combinatorial number. Okay, and then we have to substitute in the exponent and also in the coefficient the m1, m-2, etc. for the as I said, the class of the variety, so the motive of the variety. How do you do that? Okay, so this is the formula. All right. So you see, in fact, this is really the model, and this is the reason why we come with this formula. No? Okay, so we start with in the class we consider m, and m minus 1 is just taking out 1 point, taking out 2 points, and then consider the diagonal, and we end up with this geometric power structure. Okay, so this is so as I say, I put the original formula to see if, that how do we guess that was the right definition. Okay, and in fact, if we apply this formula to the series 1 over 1 minus t, we get the Capranov zeta function. So okay, so that's all right. So this is a straight definition of the formula. So the first case that we should consider. Yes. Second symmetric power, etc. Yes. Sorry, I was all right. So we have that. Okay. So properties. You have here some properties that we can deduce from the definition. First. In principle, the definition is just for the class of a variety, but can be extended or the linear combination, and also can be extended to the localization for the power of the L, where script L is the okay, and also the completion of this ring. That is really the main tool for to do what they call Motivic integration. So this can be and also it can be defined in the Grothendieck group of stacks, but I will not give the details. Okay, so but important is that the homomorphism lambda or E dot, that is the Hodge-Ley polynomial, or as I say also number of points, or as I say also number of points are what we call additive homomorphism in the corresponding of the corresponding ring to Z or the polynomials, Hodge-Ley polynomials, and then when you have a this you can get what so-called homomorphism of power structure, and that means that any formula for the involving power structure in the Motivic power structure can just get translated immediately to formulas over Z or whatever. Okay. So so what can we use for all these power structure in the Grothendieck ring? So first, for instance, is the generating series for Hilbert scheme of points. So God give an equation of the classes of Hilbert schemes in a smooth surface that can be formulated and proved in terms of power structure. So this was one of the first application. I might say also that they will give a few more applications, but I said, but the application is not only reformulate some result, but also obtain new results. So I will not say which one is new, what is just a reformulation, but we will really, with this, we obtain new results. Okay, so we can consider the, as I say, the h of x, the generated series for the schemes of Hilbert schemes. So you where Hilbert k means a Hilbert scheme of length k in x. Okay. And then you can consider the generating series, I mean, with different length, all right? And also the local ones. So hx comma little x is just the series, the scheme just centered in the point x, all right? And then the result of Gotze can be reformulated in that way that the Hilbert, the generative series for the Hilbert scheme of length k is just the local generating series, the local data point. I mean, just with the exponentiated to the class of the variety. Okay, and this is in the case of a surface. I mean, for higher dimension is not that clear, but this is one of the first results. Okay. Also, there is also compute really the generating series of the Hilbert scheme of point in the plane, a local plane. That we have this infinite product. I mean, you see that it's very simple. It only appears the class of a variety L that is appear very well, and as a consequence of the previous result, as is here, we get also the generating series for the global, for the Hilbert schemes of in the variety X. Okay, so the other application of that you will see, for instance, Chia gives a generating series of the linear polynomial on nested Hilbert schemes. Okay, here you consider a series of natural numbers, and you consider schemes of length n1, n2, etc. Nested one inside of the other. Then one get this expression for the corresponding generating series, where the R is just the number of member of the nest Okay. Okay. All right. So and also we have equivalent versions of the equivalent Hilbert schemes of under the action of a finite group. So we have a finite group acting in a variety, smooth variety. They act also in the Hilbert schemes, and then we can consider the invariant part of the action of the group, and then we have the corresponding generating series, all right? And we have a similar result, for different actions. Well, this also was worked by other people like Buriak and another. We compute the generating series when we have the action of C, this action of C star over C2, okay? Where we have this action, you will see set times sy is just set A, set B, okay, and A and B are coprimes. In our case, we have, I say, we consider this action of a finite cyclic group, okay, set P, and we have this action, sigma of X will be sigma Q to the X, and in the case where Q is congruent with -1, mod P, we have, in this case, we have a P -1 surface singularity, okay, and then we have, this gives a computation of the corresponding generating series in function of the local one. So here, I don't want to put too much formulas, but I need to put some, the computation for the local one, and this is the global one. You see, this is somehow a little complicated, but it looks at the same formula, but at the end you see there is a difference. The coefficient of L is I -1, and downstairs is +2. But again, it's just we use the fact that you can compute the second one, but exponentiating the first one. Okay, so that's all right. All right. So next, well, as I say, there are more generating functions. So, so for instance, some physicists, like 12 or 14 years ago, they consider what is the orbifold Euler characteristic, and they were much interested in this, and that is defined with these two formulas. Their two formulations are equivalent, okay, and there is also a higher order Euler characteristic. It's just when you take, instead of a pair G0, G1, you take k plus 1, take k plus 1 element of the group. And this is what is called the kth order Euler characteristic, and then we define it a generalized Motivic analog of this and we compute the corresponding generating series, okay? I mean, in terms of power structure. Here, Gn is the action over Xn is just taking the semi-direct product of I think it's Xn times G to the n. So this is I don't know how to mark this point. Oh, where is the pointer? Okay, I don't want to make. Oh, okay, so. All right. Okay. So you see, you get this formula, and then I will make a short. I don't want to make a really. I will make a sort of expose. I will just don't want to fill the screen as you had with a lot of formulas. We have more results earlier, but I will go directly to the application for other people. As I say, we have applied to much more situation. For instance, we have also the Grothendieck group of pairs of varieties, of Grothendieck group of maps among varieties, but I just, with the permission of Sabir, skip this other result. All right. So, and then I go for application to other people. So there is a really a lot of application to the what is called computation of Donaldson-Thomas Motivic invariant. So what is the original Donaldson-Thomas invariant were introduced like 20 years ago, something like that, to give a numerical count of sieves on three-dimensional Calabi-Yau varieties, okay, and then later on, okay, and then later on, Gusein-Zade Soiberman introduced a Motivic Donaldson-Thomas invariant, okay, in certain categories that are related with Calabi-Yau varieties. So, for instance, categories of how you say, sieves or derivative categories for sieves in a three-manifold. The geometric description of the power structure over stacks, in this case over a stack, really has been the main tool to compute the generating series for the Donaldson-Thomas invariant. So I will not put the formula, as I say. I will just give a list of the application. For instance, let's say if you see in Google Scholar, there is of our original paper, there is something like 115 how you say reference, and let's say more or less 90 are not from just taking out the site. There is 90 that are not from us, and there are more than 10 that are related with the computation of the Donaldson-Thomas invariant. So really, people are very interested in this computation in many, as I say, with many categories, and the main tool is really the power structure. So I will just mention a few of them without the formulas, and also without giving all the names. So there is, as I say, more than 10 papers doing that, and I will not mention all the names. So maybe one of the first application was I say, Motivic classes of commuting, commuting matrices varieties. So this is, you can consider the families of commuting varieties. There is a formula of Fate and Fine for the case of commuting matrices over finite fields. And I say this formula can be translated, the formula comes in terms of a number of points, and as I say, this kind of formula can be translated to the Motivic setting. So, as I say, this is one of the first applications. And for instance, this one, the Motivic classes of commuting matrices was essentially used for the computation, as I said, the power structure, and it was, for instance, used for several, the computation of several Donaldson-Thomas Motivic invariants. For instance, degree 0 Motivic Donaldson-Thomas invariants. There is a paper of Bryan and Morrison, and also in the thesis of Morrison, they compute several of these Motivic invariants, always using the power structure. For instance, I think this is in the thesis of Morrison, the Motivic Donaldson-Thomas invariants for conifolds, and other cases, small Krepan resolution, and also something that many people are interested in, what they call DT PT correspondence. So PT means Pandaripande Thomas invariance, and there is a very interesting correspondence. These are kind of Donaldson-Thomas invariants. Less heavy, and there is many conjecture related with this correspondence between DT and PT Motivic invariants. Okay, and again they use power structure. Another use was to Donaldson-Thomas invariants related with the Mackay correspondence, with when you have some groups, and I say okay. And then other applications are just for arithmetic and geometric properties. In fact, for many arithmetic properties, people are interested in the many arithmetic computation. People are interested in the asymptotic behavior of these invariants. So, but the asymptotic behavior means what happens when you go to infinite, and this is exactly why you can measure with the generating series. So you have in the generating series you have the values for the different parts of your computation. I mean, when the dimension or whatever, when the dimension or whatever tends to infinity, and if it happens, this generated series is rational, then you can get a lot of information. So this is, as I say, also in geometric, but also in fact, I did not say, but maybe it's in the next slide, is that, of course, we talk about the Grothendieck group of varieties over C, but there is also, this can be also defined over any field. You have the same construction over any field, and in particular, if you have a finite field, you have also another Motivic measure, not only the Euler characteristic, but you have also other Motivic measure is just counting the number of points. So they give you again, homomorphism, additive homomorphism. And I say one paradigmatic example of this is the kind of problem that asymptotic problem that interests people in arithmetic algebraic geometry is the Punen-Bertini type theorem that say for a smooth projective algebra variety X defined over a finite field give the probability that a random degree per surface H intersect transversally, and then you consider that this probability, and you consider the limited with d, the degree of the per surface, tend to infinity, and what you get is actually the Bell zeta function, 1 over the Bell zeta function evaluated the point d plus 1. So this is a really, of course, this Punen theorem, of course, was used using only arithmetic, but arithmetic algebra geometry. But for instance, Bakil was interested in a Motivic version of that, okay, and in fact, he obtained the Motivic version would use the power structure. So really, here is so there is a very fundamental paper of Bakil in which I say obtained the same result. In fact, in this paper, is Bakil and Hood. They obtained the Motivic version of the Punen-Bertini theorem, and this is the third item there. So the Motivic probability that a random hypersurface of degree d intersects transversally is asymptotically 1 over, is the same, but instead of Bell zeta function, you get Caprano zeta function instead of the value in d plus 1 minus d plus 1 is just the corresponding motif, okay? The corresponding motif, okay? But in this paper they obtain much more interesting things. For instance, the limiting motif of the space of hypersurface with a given number of singularities. They consider a given number of singularities and imposing some condition in the Taylor series and get some asymptotic study of that. And again, get some Motivic, and also there is, they try to apply to the work of Vasiliev. So he was also interested in discriminants, okay? But they explain there how in fact that was also one of the other interesting question. But this is more a question. Is not a result. But he was very much interested. Was the Motivic stabilization is symmetric power. So you consider the symmetric power. The symmetric power of x and of x, and they consider over L to ND, and the question is is there a limit of this sequence over the limit must be in the complexion of the localization. So that's but it is a very interesting question. So this is still open, okay? But and there are many other arithmetic applications. So I have to say that Bakil is very enthusiastic. Bakil is very enthusiastic about this power structure. In fact, I meet him in 2000, 2 years ago, 2033, in Chile, and he told me, you know, you are one of the guys that make this power structure. Congratulations! This is really a very important tool, and you were ahead of the time. So then I also comment that maybe we were ahead of the time, but as you remember, Sabir, at the beginning, we have difficulties with the referee because they thought that maybe, what is new here? What is the purpose of all this? More or less like lambda structure, so we don't see any interest in this construction, but you know, at the end, you see people are very much interested. Okay, so and there are other arithmetic application. For instance, there is something that is called Motivic information. So this is, I put the name in order, but maybe you can look at the paper, because I mean, I told you just without reference that there is something like the Hasselbalch entropy, Motivic mutual entropy, and Motivic information loss of a Mach. It's something completely esoteric. So I cannot, I did not read the paper, but really this exists. If you are interested in Motivic information theory, you can go to this nice paper of Motivic Mercouri. By the way, this part of arithmetic properties, you have the probability that something happens, is also called Motivic statistics. So you have the name Motivic everywhere, but there is much more application. But I didn't want to extend too much my talk. In fact, more or less, this is the end of the talk. I mean, there is other application but and as I say, now there are many applications. Even okay, and this is all. So thank you very much for the attention. Happy birthday! I mean, advance happy birthday to Sabir, and also happy birthday to all our friends of Madrid, Alejandro, Pedro, Mario, Alejandro, Pedro, Maria, Mariemi. So they all to me transmit you the happy birthday. So thank you very much.
Thank you. Any questions?
When you are speaking about Donaldson-Thomas invariants,
Yes.
Are you able to compute them in some for compact varieties, or only for local situations?
No, there is also some computation for compact varieties. But not us. I mean, there are people working on that.
I'm asking about you.
Not us. Okay, but there is really a lot of bibliography about that. Yes, but it is really. I think in some of the paper with this DT PT correspondent, there is something about that. Okay.
I have a question about equivariant Hilbert schemes. You mentioned formulas in the case of equivariant Hilbert schemes for the cyclic group. Are there formulas for other finite subgroups of SL2? Is D and E case?
There is some conjecture, but not formula. No, Sabir. No, we have some conjecture, but not the other formulas. Yes. Okay.
Okay. Okay. Maybe I have just one remark, since there was some nice review of these power structures. We'll have another talk about recent developments about power structures on Friday.
Yeah, yes.
The first talk of Friday will be by Sergei Gorchinsky, who will also talk about power structures. So everybody is welcome.
Okay.
And okay, if there are no further questions, let us thank the speaker again.
Thank you.